Welcome to this problem walkthrough. Today, we'll explore the problem titled Number of Smooth Descent Periods of a Stock. This problem focuses on identifying subarrays in a stock price sequence where each subsequent price decreases by exactly 1. We'll discuss the intuition behind solving it, potential approaches, and the trade-offs in terms of time and space complexity. Let's dive in. The problem asks us to find the total number of smooth descent periods in a stock's price data, represented as an integer array called prices. A smooth descent period is a subarray that satisfies two conditions. First, the subarray must have at least one element, and second, for every pair of consecutive elements in the subarray, the difference between the first and the next element must be exactly 1. For example, if you have two elements a underscore I and a underscore I plus 1, their difference must be a underscore I plus 1 equals 1. The task is to return the total count of all such smooth descent periods in the array. The input to the problem is the array prices, and the output is a single integer representing the total count of these smooth descent periods. Let's look at the first example to understand this better. Suppose the input array is prices equals 3, 2, 1, 4. The output in this case is 7. Here's why: every single element in the array forms a smooth descent period on its own, so we count 3, 2, 1, and 4 as 4 periods. Next, we observe that 3, 2, and 2, 1 are valid smooth descent periods, as each pair satisfies the condition that the first element is exactly 1 greater than the second. That gives us 2 more periods. Finally, the subarray 3, 2, 1 is also a smooth descent period because all consecutive elements satisfy the condition. Adding these together, we get 4 single-element periods, 2 two-element periods, and 1 three-element period, for a total of 7 smooth descent periods. Now consider the second example where prices equals 8, 6, 7, 7. The output here is 4. In this case, the only smooth descent periods are the single-element subarrays 8, 6, 7, and 7. This is because no two consecutive elements in the array satisfy the condition a underscore I plus 1 equals 1. For example, the difference between 8 and 6 is 2, and the difference between 7 and 7 is 0, so there are no multi-element smooth descent subarrays. Thus, the total count of smooth descent periods is just the 4 single-element subarrays. In the third example, we have prices equals 5, 4, 3, 2, 1. The output here is 15. Let's break this down. First, each individual element forms a smooth descent period, giving us 5, 4, 3, 2, and 1, that's 5 periods. Then, we have the two-element subarrays 5, 4, 4, 3, 3, 2, and 2, 1, which contribute 4 more periods. Next, the three-element subarrays 5, 4, 3, 4, 3, 2, and 3, 2, 1 add 3 periods. Similarly, the four-element subarrays 5, 4, 3, 2, and 4, 3, 2, 1 contribute 2 more periods, and finally, the entire array 5, 4, 3, 2, 1 is 1 smooth descent period. Summing these, we get 5 plus 4 plus 3 plus 2 plus 1 is equal to 15 smooth descent periods. The constraints ensure that the input size and values are manageable, and edge cases include single-element arrays, arrays with no valid multi-element subarrays, and long sequences that alternate between valid and invalid patterns. The solution must handle all these scenarios efficiently. To solve this problem, we first consider a brute force approach using naive iteration. The idea here is straightforward. A smooth descent period is defined as a subarray where each subsequent element decreases by exactly 1. To find all such subarrays, we could iterate through every possible subarray of the input array and check if it satisfies the smooth descent condition. Specifically, this involves generating all subarrays, then verifying for each subarray whether the condition prices, j, equals prices, j1, 1 holds for all valid indices j. While this approach is simple to implement, it is highly inefficient for large input sizes. The time complexity is O(n) squared for generating all subarrays, with an additional O(n) cost for verifying each subarray, leading to an overall complexity of O(n) cubed. This makes the brute force approach impractical for arrays with up to 100,000 elements, as it does not take advantage of the problem's constraints or properties. Instead, we need a strategy that is more computationally efficient. Now, let's look at an optimized approach using a sliding window or two-pointer technique. The key insight here is that a smooth descent period ending at index I can be extended from the smooth descent period ending at index I1 if the condition prices I equals prices I1 is satisfied. This observation allows us to count smooth descent periods efficiently without explicitly generating or iterating over all subarrays. We recognize that each individual element is always a smooth descent period of length 1. Furthermore, if the condition holds, the current descent period includes all the smooth descent periods from the previous index, plus the new subarray formed by adding the current element. If the condition is not met, the smooth descent period resets at the current index. To implement this, we initialize a counter count to store the total number of smooth descent periods, and a variable current to track the length of the smooth descent period ending at the current index. As we iterate through the array, we either extend or reset the descent period based on the condition, adding current to count at each step. This approach runs in O(n) time and uses O(1) space, making it highly efficient. An alternative approach involves using dynamic programming, which is conceptually similar to the sliding window method but differs in implementation. Here, we use a DP array DP where each element DP, I, represents the number of smooth descent periods ending at index I. Initially, we set all elements of DP to 1, as each individual element forms a descent period of length 1. We then iterate through the array from index 1 to the end. If the condition prices I equals prices I1 is satisfied, we update DP I to DP I1 plus 1, effectively capturing the cumulative smooth descent periods. Finally, we sum all values in the DP array to get the total count. While this approach is clear and intuitive, its main drawback is the additional space requirement of O(n) for the DP array, which can be avoided using the sliding window method. Thus, while dynamic programming achieves the same time complexity of O(n), it is less space efficient. Ultimately, we chose the optimized sliding window approach as our final strategy. This method leverages the cumulative nature of smooth descent periods, allowing us to efficiently compute the result in linear time. With a time complexity of O(n) and a space complexity of O(1), it is well suited for handling large input sizes. In contrast, the brute force approach, while simple, is computationally impractical due to its cubic time complexity. Meanwhile, the dynamic programming approach, though intuitive, uses additional space proportional to the input size, which the sliding window method avoids. By striking the best balance between simplicity, efficiency, and clarity, the sliding window approach is the most effective solution to this problem. To solve the problem of identifying and counting all smooth descent periods in the input array, we begin with a brute force approach. First, we initialize two key variables, n, which represents the length of the input array prices, and count, which is initially set to 0 to track the total number of valid smooth descent periods. The next step involves iterating through all possible subarrays of prices. This is achieved using two nested loops. The outer loop, with index I, starts at the first element and runs up to the second to last element, setting the starting point of each subarray. The inner loop, with index j, begins at the current index of the outer loop and extends to the end of the array, progressively increasing the length of the subarray being considered. For each subarray defined by these indices, we check whether it satisfies the smooth descent condition. Specifically, for all consecutive elements in the subarray, the difference between the current element and the next must be exactly 1. If this condition fails at any point, we stop checking further for that subarray and move on to the next one. When a subarray meets the smooth descent condition, we increment the count variable by 1 to include it in the total. Once all possible subarrays have been examined, we return the value of count as the final result, representing the total number of smooth descent periods. To better understand the concept, recall that a smooth descent period is a contiguous subarray where each element decreases by exactly 1 compared to the previous one. For instance, 5, 4, 3 is a valid example, while 5, 4, 2 is not. The brute force approach systematically examines all possible subarrays, ensuring none are missed. However, this comes at a cost. The approach has a time complexity of O(n) cubed, since it generates and checks n asterisk, n plus 1/2 subarrays, with an additional validation step for each. The nested loops are crucial to this process, as the outer loop sets the starting point while the inner loop extends the subarray to test all possible lengths. The validation step ensures that only subarrays meeting the smooth descent condition are counted. This algorithm relies on very simple data structures. The input array, prices, is used directly, and no additional storage is required to keep intermediate results. The only extra variable is count, which accumulates the total number of valid smooth descent periods. The nested loop structure is central to the brute force approach, as it ensures that every potential subarray is considered. However, the inner loop is optimized to terminate early if the smooth descent condition fails, which helps to avoid unnecessary computations. The validation step focuses on the condition prices, k plus 1 equals 1, ensuring that the subarray decreases by exactly 1 at each step. Every time a valid subarray is identified, the algorithm increments the count variable, guaranteeing that the result accurately reflects the total number of smooth descent periods found. The brute force approach comes with a high computational cost. Its time complexity is O(n cubed, driven by the triple nested loops, 2 for generating subarrays and 1 for checking the smooth descent condition. On the other hand, the space complexity is O(1), as no additional data structures are used beyond the input array and the count variable. Several edge cases highlight the importance of robust condition checking. For example, a single element array, such as 5, always qualifies as a smooth descent period, so the count should be 1. Conversely, if the array contains no valid smooth descents, such as 3, 3, 3, or 5, 3, 1, the count should be 0. For larger arrays, the brute force method becomes computationally impractical due to its high time complexity, requiring more efficient algorithms for real-world applications. Addressing these edge cases and considering performance limitations ensures the algorithm is both accurate and well-prepared for various scenarios. This solution efficiently calculates the total number of smooth descent periods in the prices list. A smooth descent period is defined as a contiguous subarray where each subsequent price decreases by exactly 1. We start by initializing count to 0, which will store the total number of smooth descent periods. A variable current_length is also initialized to 1 to track the length of the current smooth descent period. The algorithm iterates through the prices array starting from the second element, index 1. For each price, if the current price is exactly 1 less than the previous price, it extends the current smooth descent period by incrementing current_length. If the current price does not continue the descent trend, the algorithm calculates the number of subarrays within the current smooth descent period using the formula current_length asterisk current_length plus 1 / 2. This formula determines the total number of contiguous subarrays for a sequence of length current_length. After this, current_length is reset to 1 to start tracking the next sequence. Finally, after exiting the loop, the algorithm adds the contribution of the last descent period, if any, to the count. The result is returned as the total number of smooth descent periods. The time complexity of this solution is O(n), where n is the length of the prices array. Each element is traversed once, and all operations inside the loop are constant time. The space complexity is O(1), as no auxiliary data structures are used. This is the Java implementation of the number of smooth descent periods of a stock problem, mirroring the Python logic. It calculates the total number of smooth descent periods by iterating through the array and maintaining a variable to track the length of the current descent period. Key differences in Java include explicit type declarations and the use of long for handling large counts, ensuring no overflow occurs during calculations. Here, we start with the first example where the input prices are 3, 2, 1. The goal is to calculate the number of smooth descent periods. First, we initialize the variables. We set n to the length of the prices array, which is 3. The variable count is initialized to 0 to store the total number of smooth descent periods, and current_length is set to 1, representing the current descent streak. Now, in the first iteration, we check if the second price, 2, is exactly 1 less than the first price, 3. Since this condition is true, we extend the current descent streak by incrementing current_length to 2. In the second iteration, we check if the third price, 1, is 1 less than the second price, 2. This condition is also true, so the descent streak is extended to a length of 3. Now that we've completed the loop, it's time to calculate the total subarrays from this descent period. Using the formula current_length asterisk current_length plus 1 / 2, we calculate the total for a streak of length 3. Substituting the values, we get 3 by 4 / 2, which equals 6. This means there are 6 smooth descent periods in total for this example. The output is therefore 6. Next, we move to the second example where the prices are 8, 7, 6, 5, 10, 9. We start by initializing the variables. Here, n is 6 because the array has 6 elements, count is reset to 0, and current_length is set to 1. In the first iteration, we check if 7 is 1 less than 8. Since this condition is true, the descent streak is extended to a length of 2. In the second iteration, we now check if 6 is 1 less than 7. This condition is true, so the streak is extended to a length of 3. In the third iteration, we check if 5 is 1 less than 6. This is also true, so the streak continues to grow, reaching a length of 4. However, in the fourth iteration, we check if 10 is 1 less than 5. This condition is false, so the streak ends. At this point, we calculate the total subarrays from the previous streak using the formula current_length asterisk current_length plus 1 / 2. For a streak of length 4, this gives us 4 by 5 / 2, which equals 10. We add this to the count and reset current_length to 1 to start a new streak. In the fifth iteration, we check if 9 is 1 less than 10. This condition is true, so the streak is extended to a length of 2. After completing the loop, we handle the last descent period. Using the formula, we calculate the total subarrays for the final streak of length 2. Substituting the values, we get 2 by 3 / 2, which equals 3. Adding this to the count, we now have a total of 13 smooth descent periods for this example. The output is 13. Finally, we move on to the third example where the input prices are 5, 5, 5, 5. Once again, we initialize the variables. Here, n is 4 because there are 4 elements in the array, count is set to 0, and current_length is initialized to 1. Since all prices are equal, there will be no valid descent periods. In the first iteration, we check if the second price, 5, is 1 less than the first price, 5. This condition is false, so we calculate the subarrays for the current streak of length 1 using the formula current_length asterisk current_length plus 1 / 2. For a streak of length 1, this gives us 1. We add this to the count and reset current_length. The same process is repeated in the second and third iterations, where we calculate and add 1 for each streak of length 1. At the end of the loop, we add the subarrays from the final period, which is also 1. Summing all these, we find there are 4 smooth descent periods in total for this example. The output is therefore 4. The time complexity of our solution is O(n), where n represents the number of elements in the input array prices. This is because the algorithm uses a single for loop to iterate through the array, starting from index 1 and running until the end of the array. Since the loop performs a constant amount of work for each iteration, this contributes O(n) to the overall time complexity. Inside the loop, the algorithm checks if the current price continues a smooth descent by performing a simple comparison, which takes O(1) time. Additionally, when a descent period ends, the formula current_length asterisk current_length plus 1 / 2 is used to calculate the count of subarrays for the completed descent. This formula is a constant time operation, O(1). Finally, resetting the current_length variable also takes constant time, O(1). These operations inside the loop do not depend on the size of the input, so they do not increase the time complexity beyond O(n). After the main loop finishes, the algorithm performs a final addition to account for the last smooth descent period. This uses the same constant time formula, current_length asterisk current_length plus 1 / 2, which also contributes O(1) to the time complexity. Since the total work is dominated by the single traversal of the array, the overall time complexity remains O(n). Moving on to space complexity, the solution is highly efficient and uses O(1) space. The input array prices is provided as input, but no additional data structures or arrays are created. Instead, the algorithm only uses a few auxiliary variables, such as n, count, and current underscore length. These variables require a constant amount of memory, regardless of the size of the input. Therefore, the space complexity is constant, or O1. The space complexity of our solution remains O1, as no additional memory is needed apart from a few variables. To put our approach into perspective, let's compare it to a brute force solution. A naive approach would involve iterating through all possible subarrays of prices and checking whether each subarray represents a smooth descent. Generating all subarrays would take n squared time, and checking each subarray for the smooth descent property could add an additional k, where k is the length of the subarray. In the worst case, this could result in an n cubed time complexity. In terms of space, the brute force approach would require O1 space if subarrays are checked in place, but explicitly storing all subarrays would increase the space complexity to n squared. In contrast, our optimized solution eliminates the need to generate subarrays and dynamically calculates the contribution of each smooth descent period using a single traversal. This reduces the time complexity to n, while maintaining a space complexity of O1. Analyzing the best, worst, and average cases, the algorithm consistently demonstrates n time complexity. In the best-case scenario, if all elements in the prices array are part of a single smooth descent, the algorithm still processes the entire array once, resulting in n time complexity. Similarly, in the worst-case scenario, where no smooth descent periods exist, e.g., if every element breaks the descent, the algorithm still traverses the array once, so the time complexity remains n. On average, the algorithm performs the same number of operations per element, which means the time complexity is n in all cases. Mathematically, the total work done by the algorithm is proportional to the number of elements in the array, as each element is visited exactly once. Since the constant time operations inside the loop do not depend on the size of the input, and there are no nested loops, the overall time complexity is conclusively n. When solving this problem, there are several common pitfalls to watch out for. First, incorrect handling of edge cases can be an issue. For example, if the array of prices has fewer than 2 elements, it's impossible to have any smooth descent periods, so these cases need to be explicitly addressed to prevent runtime errors. Next, be cautious about resetting the counter prematurely. If the current price is not exactly 1 less than the previous price, the descent period should end, and failing to reset the counter at this point can lead to inaccurate results. Another mistake involves using nested loops, which is a brute force approach. While it might seem straightforward, this method results in n squared time complexity, which is highly inefficient for larger arrays and can cause the solution to time out. Finally, off-by-one errors in subarray calculation are a frequent source of trouble. Remember, a descent period of length k contributes k plus 1/2 subarrays. Misunderstanding or overlooking this can lead to incorrect totals, so it's important to compute contributions carefully. Additionally, skipping continuity in the descent is another common mistake. Smooth descent periods require that the difference between consecutive prices is exactly 1, meaning prices I1 must equal 1. Failing to verify this condition can result in subarrays that don't actually qualify as smooth descents being included in the count. Now, from an interview perspective, there are several valuable insights to consider. First, identifying patterns in array problems is key. Many such problems revolve around finding contiguous subarrays that meet specific criteria, and techniques like maintaining a running count or a sliding window can significantly optimize performance. Pre-computing contributions is another technique to explore. Instead of recalculating the contribution of each subarray individually, you can use mathematical formulas like k plus 1/2 to save time. Optimal space usage is also crucial, as problems like this often require extra space. This means you should focus on tracking necessary states, like the current descent length, without resorting to additional storage. Lastly, always be prepared to discuss trade-offs. Highlight why optimized solutions, such as n approaches, are critical for scalability and explain the limitations of brute force methods. There are also several related problems that can help you build a deeper understanding of these concepts. For instance, LeetCode 152, Maximum Product Subarray, uses a similar sliding window approach to identify subarrays with specific properties. LeetCode 53, Maximum Subarray, focuses on optimizing contiguous subarray calculations, which is closely aligned with the techniques used in smooth descent problems. Then there's LeetCode 238, Product of Array Except Self, which emphasizes efficient state tracking to avoid unnecessary computations. Lastly, LeetCode 209, Minimum Size Subarray Sum, is another sliding window problem that reinforces the importance of these techniques in different contexts. Now, in terms of alternative approaches, the sliding window method is a highly efficient way to track descent periods. Using this approach eliminates the need for recalculating contributions repeatedly, but it does require careful management of edge cases to ensure correctness. Another option is cumulative contribution calculation, where you pre-compute the contributions for all possible descent lengths. This can make your solution faster, but it comes at the cost of additional memory usage. Each approach has its trade-offs, so it's important to choose the one that best fits the problem constraints and requirements. Great job making it to the end of this walkthrough. We reviewed the problem, discussed approaches, and highlighted key takeaways. Remember to practice similar problems to solidify your understanding. If you enjoyed this, don't forget to like and subscribe for more content. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!